Okay, guys, I was asked to record this video. I didn't record a video on this section at all because I feel like I didn't really explain, but maybe for 5-minute increments. But on this video, what I'm going to do is I'm going to work through everything regarding rational exponents from the book, chapter 6.2. And I'm going to go straight through the odds, every single section that we've covered in class. And hopefully by the end of this, you actually understand it a little bit better. I'm going to be flipping back and forth between this book right here and also this sheet of paper. I'm just going to copy down a problem one at a time and then work it out. So starting off, it says to use the properties of rational exponents to simplify the expression. All right, so the properties of rational exponents, if you flip 2 pages back on page 296, here are the properties, okay? So if you're watching this video and you want to watch the properties as you're watching the videos, then take a picture of that. Just pause the video, take a picture of it, so you can look at your phone at least. But there's the properties. I'm going to be referencing these properties as I actually do these problems. So starting on number 3. Number 3 says 9 squared to the, I think it's 1/3. That's a 3. That's awful looking. So 9 squared to the 1/3 power. Give me just a second. Anna, that's yours. Okay. So 9 squared to the 1/3 power. Pretty much what you see here, if you're looking at those rules or those properties, is you see a power to a power, which simply means you're going to multiply. The rule looks like this. It says if you have a to some power m, then that to the n power, then that's the same as doing a to the m times n. So pretty much I have a, which is 9, to the 2 times 1/3. So to the, I can write it like this, 2 times 1/3. So again, that's 9 to the 2/3, and that's the final answer. And I'm done with number 3. So number 5 now. Number 5 right here says 6 divided by 6 to the 1/4. So number 5 is 6 divided by 6 to the 1/4. Now, I guess since I'm recording a video from scratch, here's generally the questions that I ask myself as I'm kind of going through these properties that you took a picture of a second ago. One is, am I looking at a product where 2 things are being multiplied like you see here, or maybe like you see here, 2 things are being multiplied? Or am I looking at a quotient where 2 things are being divided like you see here, or like you see here? Am I looking at a product or a quotient? And then the next question I'm going to ask is, all right, if I'm looking at a product, are my bases the same, like A and A, or are my bases different, A and B? Are my exponents the same, like you see here, M and M, or are my exponents different, like you see here, M and N? And the same thing for the quotients. Are my bases the same, or are they different? Are my exponents the same, M and N, or are they, well, I guess that's different. Are they different, M and N, or are they the same, M and M? Okay, and those are the questions that kind of help you just see through all this stuff. So if I have 6 divided by 6 to the 1/4, then first question, is it a product or is it a quotient? It's a quotient. Are my bases the same or are they different? Are my exponents the same or are they different? So it's a quotient, and you have a quotient rule that looks like this. A to the m divided by a to the n, where both my bases are the same. So I see 6 and 6. I have one exponent, then I have a different exponent on the bottom. Well, that's the same thing as a, let me write it like this, a to the m minus n. So what that means is this is 6 to the 1 minus 1/4. And that equals 6 to the 3/4. 1 minus 1/4 is 3/4. Okay, going on to number 7. Number 7, this is kind of a semi-tough one. I'm going to go a lot quicker with it, though. So 8 to the 4th divided by 10 to the 4th, and all of that is to the negative 1/4. All right, so there's number 7. There's a rule, quotient rule. Again, first question, is it a quotient? Yes. Second question, are the bases the same or are the exponents the same? The exponents are the same. Okay, so there's a rule that says if I have a quotient, but with different bases, a and b. Different bases, but I have the same exponent. And that's the same thing as a divided by b to the m power, like that. So that's what I'm going to do. I'm going to write this as 8 divided by 10 to the 4th power. 8 divided by 10 to the 4th power. And now don't forget that I have this little negative 1/4 on the outside. So I still have all of that to the negative 1/4. Okay, next thing it talks about is the power rule. So I'm going to reference the properties, and I'm going to do the power to a power. So that rule states that I can multiply these two exponents together. 4 times negative 1/4, that equals 8 over 10. 4 times negative 1/4 is to the negative 1 power. 4 times negative 1/4 is negative 1. Okay, now anything to the negative 1 power, the property is going to tell you that it's anything to the negative 1 power, like a to the negative 1, is 1 over a. Now, if you've been paying attention in class, pretty much you start catching on that anything to the negative 1 power is just a fraction flipped. So it's the same thing as 10 over 8. I'll reduce that to be 5 over 4. And that's the final answer there. All right, on to number 9. So, number 9 from the book says 3 to the negative 2/3 times 3 to the 1/3, like this. Then it has it to the negative 1 power. Okay, so there it is. There's number 9. All right, so I have a product here. So I'm looking at the top of that property list that I told you to take a picture of at the beginning of the video. I'm looking at the top. It's a product. Also, my bases are the same. So there's a product rule. One of those two product rules says if my bases are the same, so I have a to the m power times a to the n power, then that's the same thing as a to the m plus n. Like that. There's a rule that says that. And that's what I have here. I have 3 to m, and I have 3 to n. So that's the same thing as 3 to the m plus n. So I have 3 to the m plus n. Okay, and then I still have that little negative 1 on the outside. So m plus n, okay? So that's going to be 3. Negative 2/3 plus 1/3 is negative 1/3. And then I still have the negative 1 on the outside. And again, we keep using this rule, so you should pretty much memorize it. If you have a power to a power, you just multiply them together. So that's the same thing as 3 to the positive 1/3. Okay, so going on. Next one. Number 11. 11 says 2 to the 2/3 times 16 to the 2/3 divided by 4 to the 2/3. So this has a little bit of both things going on. You have a product and you also have a quotient. I'm going to start off with the top, and I'm going to use the product rule where it has different bases but the same exponent. So I'm not going to write it out. It's the one that says a to the m times b to the m. So same exponent but different bases. Is the same thing as a times b to the m. So it's 2 times 16, which is 32, to the 2/3 divided by 4 to the 2/3. Now I'm going to start using the quotient rule. There's a quotient rule that says, okay, well, if I have a to the 2/3 and I have a different base, b to the same exponent, 2/3, then you have a divided by b, so 32 divided by 4 to the 2/3. And 32 divided by 4 is 8 to the 2/3. Now, in most cases, you'd be done here, but the point is that 8 to the 2/3 is actually the same thing, and we learned this in a previous lesson, as the third root of 8 squared. That's the same thing. Well, we know what the third root of 8 is. The third root of 8 is 2. 2 times 2 times 2 is 8. So this is the same thing as 2 squared. And we know what 2 squared is. That's 4. So sometimes you're going to have to simplify a little bit further than you normally would at other times. If you can, you simplify further. Okay, that was number 11. So now we're done with this section. If you want some practice, you can pause the video and take a picture of 4 through 12 and practice those on your own. Reference those same properties. Now, 13 through 15, pretty much the properties that it's referencing are on page, let's see, right here. Page 297 at the top. And again, you can pause the video and you can take a picture of these properties right here. And it pretty much says, under one condition, that your roots are the same degree. But if you have the nth root of a times the nth root of b, when your roots are the same degree, you can write them all under one big root. Or if you have one big root, two things multiplied by each other underneath, you can break that up into two separate ones. So you can go either from two separate to one big, or you can go from one big to the two separate. Same thing with quotient. You can do one big quotient to two separate quotient, or two separate, like a numerator and denominator. Or you can go to two separate to the one big. Okay, so it's referencing those. Let's go ahead and do them. Let's see, number 19, no, 13 through 19. All right, I'm going to go ahead and rip this page out real quick. Okay, so number 13. Well, okay, so I have a square root of 2 times a square root of 72. So because they're both square roots, I can just multiply them together. And 2 times 72, that's 144. And we know the square root of 144 is 12, and that is as simple as that, actually. All right, number 15, you have a fourth root of 6 and a fourth root of 8. So because they're the same degree root, I can multiply them together. So I end up having the fourth root of 48. Now, when I have the fourth root of 48, sometimes, again, you can break these down. When you see a number like 48, you kind of get suspicious because it's such an even number. So it's like, all right, divide it by 2. And I taught you guys this in class, so I'm not going to explain this concept. 12, 2 times 6, 2 times 3. Okay, so I break 48 down, and it ends up being this right here. 2 times 2 times 2 times 2 times 3 is the same thing as 48. So I have the actual fourth root of 2 times 2 times 2 times 2 times 3. All right, now here's the deal. If I'm pulling out fourth roots, that is a perfect fourth root. 2 times itself 4 times creates a perfect fourth root. It's actually 16. And I can pull out all 4 of those 2's, take the fourth root of that number, which is just 2, and write it like that. Okay, now just a quick aside, if you're taking a fourth root, then you're pulling out groups of 4. If you're taking a third root, pulling out groups of 3. If you're taking a 52nd root, then you're pulling out groups of 52, which is huge. You're not going to really do that reasonably, but that's the point. Depending on the degree of the root will dictate how big the groups are that you need to pull out. Okay, that was number 13. No, that was 15. Okay. Number 17 says, all right, you've got a fifth degree root, so you can actually divide these two numbers. So just to write it in a more simple way, number 17, you end up having the fifth root of 486 divided by 2. And 486, that's a terrible 486, but I think if you're listening while watching this video, you understand that's a 486. Okay, 486 divided by 2 is 243. 243. Okay, you can leave your answer like that, but the thing is you can actually simplify that further. Now, when you look at the number like 243, that's not one that actually raises suspicion in me that I can simplify, but the fact of the matter is that you can simplify that further. So you break it down. Maybe by chance you can break it down and find the pair of 5, like 5 of something, because it's a fifth root. So I'm going to divide by 3. 3 times 81 is that, okay? What about 81? I'm going to break that down. Well, 81 is just 9 times 9, and honestly, you can keep dividing by 3, and you'll see that. You can, but I realize 81 is 9 times 9, and I realize 9 is 3 times 3, and this 9 is also 3 times 3. So the fifth root of 243, the fifth root of 243 is the same thing as the fifth root of 3 times 3 times 3 times 3 times 3. 5 of them. 1, 2, 3, 4, 5. That's the same exact thing. Except now, because it's a fifth root, I'm looking for groups of 5. So I have 5 3s here, so I'm going to pull them all out. That creates a perfect fifth root. And my answer is actually just simply 3, because there's nothing left under the fifth root to put down there. So you just leave it at 3. Okay, number 19. I'm going to go ahead and write number 19 right here next to it. I'm not going to write it. I'm just going to go from here. So I have a third root of 6 times a third root of 72. And because they're both third roots, then I can go ahead and multiply that. Unfortunately, I don't know what that is. Can somebody with the calculator real quick multiply 6 times 72? 432. Okay, so you end up getting the fourth root, or the third root of 432 divided by the cubed root of 2. And because they're both cubed roots, I can go ahead and... Can you guys actually see this on the screen? I can't tell. Somebody's standing in front. Somebody. I won't list that somebody's name, but I can't see. All right. Anyway, so 432 divided by 2, I can do that because it's the same degree root. That is going to be the cubed root of 216. 216. Okay, and if you break 216 down by dividing by 2, and you continue breaking it down, you keep breaking it down, you find out that actually you get 2 times 2 times 2 times 3 times 3 times 3. And that ends up being the cubed root of 216. And you have 3 2's and you have 3 3's. And there's nothing left actually underneath that any further. So if I have 3 2's and 3 3's and I break that down, then I have 2 times 3, which is 6. And the cubed root of, well, there's nothing left down here. So I don't even have the cubed root of anything. It's just straight up 6. And that's the answer. Okay. I want to pause here in the video and say if anybody has questions about any of those two sections, you can feel free to come in. I'm always here early in the morning. You can come in early in the morning and I can help you with it. Now, going on to number 21 through 27. This is simplifying radicals. So there's two types of simplifying. One of them I already talked about. Like that one, you just kind of break down the number over and over and over until you pull out groups of 4. But then there's also the simplifying radicals that are in the denominator, and that's called rationalizing. Okay, so to rationalize the denominator, well, I'll do that. I'll explain the concept when I get to number 23. All right, so 21. You have a fourth root of 567. Unfortunately, I guess I'm just going to have to break this down. So, let's see, 567 maybe divided by 3. I'm going to grab a calculator for myself. Okay. So, 567 divided by 3 is 189. So 3 divides that, and it equals 189. Okay, 3 divides that also. That's going to be 3 times 63. 3 divides that. That's 3 times 21. 3 divides this. That's 3 times 7. So I end up getting 3 times 3 times 3 times 3 times 7 is the same as this. So it's actually 4 root 1, 2, 3, 4 3's times 7. And I'm looking for groups of 4. Guys, this is practice. This is why it works out so ideally like this. So here it is, 4 3's. So I have a group of 3's times the fourth root of 7. And that'll be the final answer. Notice the 7 stays under the fourth root. I have one perfect fourth root here. And it's 3 times 3 times 3 times 3, which is actually 81. So I have 3 times the fourth root of 7 as my final answer. Okay. Starting on a new sheet of paper. This is getting crowded. Okay. Number 23. So the problem with this one is you have a fourth root, or a cubed root in the denominator. So I need to do something that we call rationalizing the denominator. Okay, so I have to get rid of the radical out of the denominator. And the way to do that is, notice it's a third root. So I want to create a perfect third root, or cubed root, in the denominator. So I need to realize what 4 is actually, the components of 4. What is 4 made out of? Well, 4 is actually, I'm going to erase that. 4 is actually 2 times 2. That's what 4 is. So here's the cube root of 4. I didn't change anything, I just changed the way it looked. That's the cube root of 4. All right, now this is almost a perfect cube root. I actually just need one more 2 there. And then I could pull out a group of 2's, and it would be a perfect cube root at that point. So what I'm going to do is I'm going to add a 2 on the bottom, but I can't just decide to add a 2 because that would change the value. So I'm going to multiply by 1. Multiplying by 1 does not change the value. So what I have up top is the cube root of 5 times the cube root of 2. That gives me the cube root of 5 times 2, which is 10, over the cube root of 2 times 2 times 2. So let me just write that real quick. Cube root of 2 times 2 times 2. Now notice what I did. Now I have 3 2's down here. So I created a perfect cube root. So the cube root of 2 times 2 times 2 is simply, hopefully you've guessed it before I tell you, it's just 2. And in my denominator, I don't have a radical anymore. And that's the final answer. Sometimes you can break this down further, but the cube root of 10 cannot be simplified any further than it already is. All right, next one, cube root of 3 divided by cube root of 8. Or square root, I'm sorry, square root of 3 divided by 8. Let me just rewrite that. So here it is. Square root of 3 divided by 8. Now here's the deal. You can take something like the square root of 3 divided by 8 and write it like this. That's the square root of 3 divided by the square root of 8. Now the problem is you have a square root in the denominator, so you need to get rid of it. There is no perfect square root of 8, so what I'm going to do is actually multiply by the square root of 8 over the square root of 8. And in doing so, remember I'm multiplying by 1. That's the trick, because I'm not changing the value. But in doing so, I have the square root of 3 times the square root of 8, which is the square root of 24, divided by the square root of 8 times 8. And I'm pulling out square root, so I'm pulling out groups of 2. So I created a perfect square root. 8 times 8 is 64. So I have the square root of 24 divided by 8, like that. I must be in a happy mood because I'm writing upward for some reason. But here we go. Square root of 24, you can actually break this down too. And you should be suspicious that you could. So 24 is, let's see, 2 times 2 times 2 times 3. That's what the square root of 24 is. Divided by 8. Okay, let's start bringing this back down. Here we go. All right, so 2 times 2, there's a pair of 2's. So this is the same thing as 2 times the square root of 2 times 3 is still under there. That's 6 over 8. And one last simplification. 2 divided by 8 could be simplified to be 1 over 4. So I have the square root of 6 over 4. All right, that's a lot of simplifying. Sometimes things are that complicated, sometimes they are not. But hopefully you understood every single one of those steps. If not, go back, watch that again, because it all does make sense. Okay, number 27. Number 27. Oh, I get to address something that people had a lot of misconceptions about on number 27. So, this says the cube root of 64 divided by 49. All right, cube root of 64 divided by 49. Well, that's the same thing as the cube root of 64 divided by the cube root of 49. Now, the problem with this is 49 is not a perfect cube root, and I have a radical in the denominator. 49 is close to it, though. It's 7 times 7. So if I wanted to make it a perfect cube root, right now I have the cube root of 7 times 7. I need one more 7. So I'm going to multiply by the cube root of 7 on top and the cube root of 7 on bottom. Now I have the cube root of 64. Guys, I'm going to just think, I didn't realize this actually, but the cube root of 64 is something solid. It's 4. So that's 4 times the cube root of 7. So notice, if you're confused about what I just did, I recognize that the cube root of 64 was 4, so I wrote it right here. And the cube root of 7 is nothing fancy, so I just rewrote the cube root of 7 right there. So it's 4 times the cube root of 7 on top. On bottom, I have the cube root of 7 times 7 times 7. The cube root of 7 times 7 times 7, which is actually, I think, 343. It's a perfect 7. So I have, as my final answer, 4 times the cube root of 7 divided by 7. Still writing upward for some reason. All right. I'm going to go ahead and flip this paper over so I stop writing upward. All right, here we go. That's number 27. 29. All right, so 29. This is an interesting type of problem. So I'm going to introduce the concept of a conjugate. So why you have to use a conjugate is based on everything that I just taught you, you might be suspicious to simplify something like this. Maybe you multiply by the square root of 3 over the square root of 3. By the way, if you're watching this video, I'm going to tell you now before I start doing this too far, that is not the way to do it. Okay? I'm just telling you what's wrong with this idea. 1 times the square root of 3, because remember, you're trying to get rid of any kind of radical in the denominator. But 1 times the square root of 3 is the square root of 3 in the numerator. Then square root of 3 times square root of 3 is 3. Great. Maybe you did what you wanted to do. So you got rid of that radical. But also, don't forget to do square root of 3 times 1. So you end up getting the square root of 3 plus 3. And you just shifted it from this square root over to the other one. All right? So that creates a problem all on its own. We have another square root. All right? So we can't multiply by square root of 3 over square root of 3. So let me start over. This is how you do that. And it's actually very similar to, let me write it there. Here's a side note on the video. It's very similar to x squared minus 64 and factoring a difference of squares. Because to factor it, you do x plus 8 times x minus 8. And the reason you do the plus and the minus is because this doesn't actually have a center term. So x times x is x squared. X times negative 8 is negative 8x. 8 times x is 8x. 8 times negative 8 is negative 64. And these cancel. That's the important thing to notice about the difference of squares. It's the same thing when you multiply by a conjugate. You're trying to get something to cancel out. So in order to get it to cancel out, notice difference of squares was, real quick, one more time, x plus 8x minus 8. So when I get rid of this right here, I'm multiplying by 1 minus square root of 3 over 1 minus square root of 3. It's called the conjugate. Okay? Notice all I did was I'm multiplying by the exact same thing, except instead of a plus, I have a minus sign. Now, the reason I do that is because when I multiply all this out, it ends up being 1 times 1 is 1. 1 times negative square root of 3 is negative square root of 3. So you have that divided by 1 times 1 is 1. So keep in mind, we have to distribute. So 1 times 1 is 1. 1 times negative square root of 3 is negative square root of 3. Positive square root of 3 times 1 is positive square root of 3. 3 times negative square root of 3 is negative 3. Now, what's interesting, and the relationship between this and difference of squares, is that this cancels with that. And that's what you're hoping for. So in the denominator, you have 1 minus 3. So you have a negative 2 in the denominator, and on top you have 1 minus square root of 3. And you've gotten rid of your radical from the denominator. So let me do it maybe one more time, and then I'm going to kind of move on really quick. So let me do it on a complicated looking one, like 33. So 33 is 9 divided by square root of 3 plus the square root of 7. Okay, so let me move this book, actually. It's been bothering me the whole time. I'll just finally get rid of it. All right. So square root of 3 plus square root of 7 is in the denominator. So to get rid of that, I multiply by the conjugate, which is truly, don't It's simply switching the sign. Divided by square root of 3 minus square root of 7. Now what does this equal? You have 9 times square root of 3, which is 9, square root of 3, minus 9 times square root of 7, minus 9 square roots of 7. All right, so that's the top, that's the numerator. And the denominator, I have square root of 3 times square root of 3, which is 3. I have square root of 3 times negative square root of 7. So I have negative square root of 21. Plus square root of 7 times square root of 3, which is positive square root 21. And then minus square root of 7 times square root of 7, so minus 7. So it equals 9 square roots of 3 minus 9 square roots of 7 divided by, these cancel, 3 minus 7 is negative 4 as a final answer. Okay, I'm actually going to stop the video there. Hopefully that helped a lot. I just went through pretty much every concept you need to know in order to do this. Actually, here, I lied. One more concept. This is going to be really easy. I don't need to explain it, though, too much. So 9 cube roots of 11 plus 3 cube roots of 11. How many cube roots of 11 do you have? You'd have 12 cube roots of 11. In order to do that, you need to be adding the same thing. Notice you're adding cube roots of 11. This one, you have 3 11 to the 1/4 plus 9 11 to the 1/4. So you're adding the same thing. You end up having 12 11 to the 1/4. 5 square roots of 12 minus 19 square roots of 3. You can't subtract those from each other until that is square roots of 3 as well. So you break 12 down. It ends up being 2 times the square root of 3. So what it actually is 5 times 2 square root of 3 minus 19 square root of 3. 5 times 2 is 10. So you have 10 square roots of 3 minus 19 square roots of 3, which is negative 9. Square roots of 3. I wish I could explain that a little bit better, but if you watch that and you listen to every word that I'm saying, that'll probably make sense. Okay, so the trick is break down your square roots or whatever these are. Don't forget this is actually a square root also. This is a cube root of 24. So break down all of your roots until they look the same so you can add or subtract them, and that would be the end of that story. Anyway, guys, if you need help, again, I'm here every morning, 7 to 7:15 in the morning, so come by and get some tutoring.